Hello and welcome to Aromatic Asthmatic Office Hours Week 2, Spring 2021. Um, as always, I'm here to take any questions, any live questions you may have. In the absence of any, I'm going to check my emails. I did about, what time is it? It's just a little past 12. I did about maybe an hour ago, hour and a half ago. And hadn't received any office hour questions. I'm going to do that right now. Double check my emails, see if any new questions came in. But as always, I'll totally prioritize any of you who are here live. I want to answer your questions first. So if you have any, hit me up. If not, it'll be a video of me once again drinking coffee. All right. I want to know. Do you have any questions? All right. Oh, hold up. Sorry, I'm noticing something might be off with the stream. The aspect ratio looks super out of whack. Let me take a look. Oh, no, it looks okay. Okay, it was just showing up weird on the on my display, but I guess it's fine. All right. Well, that's a relief. All right, let's see. Hey, Ashley. I totally can. Okay, so and real quick, okay, so we have a Chem 400 question coming in specifically about percent mass. Okay, solid. All right, so first off, percent mass is something that we run into in this class fairly frequently, and this won't be the only time you experience it, but this is kind of the first introduction. Spilled coffee on my pen tablet. That's always fun. All right, so percent mass in general. So this is kind of generically, and then I'll get to the specific problem that you're asking for. But percent by mass is the mass of a part divided by the mass of the whole, whatever it is we're talking about, multiplied by 100. That is the kind of general expression for percent by mass. Now, if we're talking about the percent mass of an element, in a compound, and this is the first instance where it shows up in our Chem 400 lecture, that's going to be equal to the mass of that element divided by the molecular weight of the compound times 100. And you can see that this fits into kind of the general form that we wrote up here. It's the mass of a part, which is the mass of just that element, over over the mass of the whole, which is the molecular weight. So, for example, let's do a concrete example here. So let's find the percent mass of oxygen in carbon dioxide, CO2, right? So the way we tackle this is, again, we know that our equation is the mass of oxygen atoms in the compound, over the mass of the whole. Now, we're going to need to calculate the molecular weight for carbon dioxide, and to do so, we need to add up the mass of every atom in the molecule. So carbon has an atomic mass of 12.01 AMU. Oxygen has an atomic mass of 16.00 AMU. But the thing to remember here is there are 2 oxygen atoms. So we need to multiply 16.00 by 2 because we actually have 2 of them in the compound. So once you do, our total mass of both oxygen atoms will be 32.00 AMU. Now we can add these together to get the molecular weight of carbon, which comes out to be, sorry, not of carbon dioxide, 44.10 AMU. All right, once we know the molecular weight, now we can actually calculate our percent mass. So this is the percent mass of oxygen is mass of the part over mass of the whole. Now, oxygen, as we know, has an atomic mass of 16.00 AMU. But just like before, we have to take into account the fact that there are 2 oxygen atoms in this molecule. So if we're calculating the percent mass of oxygen, we need to incorporate the fact that there are 2 oxygen atoms. So it's going to be 2 times 16 over our molecular weight, 44.01 AMU times 100. All right, so now we bust out whatever trusty calculator you have on hand. And let's see, we go 2 times 16, so that's 32, divided by 44.01 times 100. All right, so my calculator is telling me, giving me a value of 72.71075. The number keeps going, but we don't have to, because when you look at our sig figs, in the numerator of this expression, we have 1, 2, 3, 4 significant digits. In the denominator, we have 4 significant digits, so our answer can only have 4 significant digits. So we count off the first 4, 1, 2, 3, 4. 0 rounds down. So the percent mass of oxygen is 72.71%. One thing you'll notice about the units is you have atomic mass units in your numerator and denominator, so they cancel, which makes sense because percentage doesn't have units, it's just a percent. And so our answer for what's the percent mass of oxygen in CO2 is 72.71%. Actually, did that make sense? Slash, did that answer your question? If not, if you're like, okay, I get that, but there's still parts of it I don't understand, I totally want to unpack it for you. So you let me know, and we'll dig as deep into it as you want to go. Awesome. That is excellent. All right, let's see. An exam level empirical formula and molecular formula. Okay. Yes. Let me give me a moment to cook one up. Okay. All right, so let's do an empirical formula part. An empirical formula problem. Give me a second here while I rearrange the screen. Okay. Okay. So here's the example. Let's see. An ionic compound is found to be composed of 68.4% chromium and 31.6% oxygen. Determine its empirical formula. All right, and this would be like a part A, and then once we have the empirical formula, I'll write the portion of the question that deals with the molecular formula. All right, but we always got to start with empirical. All right, now, there are two ways that empirical formula problems can be presented to you. Either way can totally show up on the exam. In fact, it's most likely that both will. You can be given the masses, be told, oh, this many grams of chromium, this many grams of oxygen, or you could be given the percentages as we are here. And whenever you're given the percents of each element, the way you move forward with solving the problem is you assume that you're dealing with 100 grams. Because if you have 100 grams, that means you will have 68.4 grams of chromium, and you will have 31.6 0.6 grams of oxygen. All right, if your total mass is 100 grams. All right, so now that we have starting masses for chromium and oxygen, the next step is to move to moles, because remember, we're trying to find the empirical formula, which is going to be Cr with an X subscript. We don't know what that subscript is. O, Y. And both of these quantities, both X and Y, these are molar quantities. These are moles right here. It doesn't give us a mass ratio between chromium and oxygen. It gives us a molar ratio between the moles of chromium atoms present in the molecule and the moles of oxygen atoms. So we need to convert both of these quantities from grams to moles. And we do this using the atomic mass given to us on the periodic table. Now, chromium, I don't have that one memorized, has an atomic mass of 51.996 grams of chromium. Oxygen has an atomic mass of 16.00 grams in a mole. All right, so grams of oxygen cancel, grams of chromium cancel, and now we can crunch our numbers to find how many moles of each are present. So busting out our calculators, I've got 68.4 divided by 51.996. So I have 1.31548 moles of chromium. And let's see, 31.6 divided by 16.00 is 1.975 moles of oxygen. Now, sig figs wise, we have 1, 2, 3, 4, 5 in our denominator for chromium, 4 in our denominator for oxygen, but the percentages we're given for chromium only has 3 sig figs. For oxygen, it has 3 sig figs, so that will limit our significant digits. Now, I'm going to wait to round to the end, but I'm putting these lines here to remind myself that each of these numbers only has 3 significant digits. All right, now, all right, so all right, I'm just gonna snap, there we go, the picture so I have those for reference because I have to clear the board. Now that we know the molar quantities of each compound, we can plug in these values for both X and Y. So we're going to have chromium with a subscript of 1.3154. It keeps going. And oxygen with a subscript of 1.7975. And again, 3 sig figs in each of these, though. The nice thing about the empirical formula problems is This is one of the rare instances where we don't have to worry too much about sig figs. All right, so this is the correct ratio for the empirical formula. The problem is, as you already know, molecular formulas, empirical formulas, you can only have integer numbers. So we have to figure out what integers go in these subscripts. And the first step in doing that is you want to divide both molar quantities, because we don't want to mess with the ratio. Excuse me. We're going to divide both of them by the smaller of the two numbers, 1.3154. Once we do that, the subscript for chromium is going to be 1, right? Because 1.3154 divided by 1.3154 is 1, right? And then the subscript for oxygen, we actually have to crunch those numbers because I can't do that math in my head. 1.975 divided by 1.3154 comes out to be 1.5. It's 1.50144444 forever, but we don't have to worry about that because, again, these are going to come out to integers. All right, now, we know our ratio is 1 to 1.5. The problem is you are never allowed to have a decimal or a fraction as a subscript in an empirical or molecular formula. So what we got to do here is we need to convert this to an improper fraction. Sorry, I thought my phone was on. Oh, it is on silent. I don't know why it's vibrating then. All right, let's convert that to an improper fraction. And you'll see why in a minute. Or I'm going to write it right here. So we're going to have chromium. 1.5 is 3/2. And the reason why we're converting this to an improper fraction is whenever you are whenever you have a decimal, a fraction in your subscript for your empirical formula, you want to convert to an improper fraction so that you can multiply both subscripts by your denominator and get rid of your denominator. So we're going to multiply both of these by the same thing, again, because we don't want to mess with the ratio. And this is going to give us our empirical formula. It's going to be Cr2O3. And that is the empirical formula for this ionic compound. How's it going so far? Before we kind of shift gears, jump into molecular formula mode. I'm going to real quick calculate the next part of this problem. All right. All right. Actually, if you oh, okay, there we go. Okay, got this. Oh, dude. Well, stinking done. Well, stinking done. If you're working the problems faster than me, then that means you are ultra competent. All right, let's take a look at the next part of this problem then. All right, so this will be, oops, this will be part B. If this compound has a molecular weight of 304 AMU, what is the molecular formula? For this compound. All right. Now, the way you find, so to find the molecular formula, you can do this if you know the empirical formula and the molecular weight. And here's why. We know that the difference between a molecular formula and an empirical formula is a scalar factor. So, for example, if your empirical formula is C1H1 and the molecular formula is C6H6. The difference between the empirical formula and the molecular formula is a factor of 6, right? If you took the empirical, if you took the empirical formula and multiplied your number of carbons and your number of hydrogens by 6, that gives you the molecular formula. Right? So the factor that you multiply each atom in the molecule by to go from the empirical formula to the molecular formula is 6. And how you find N is you take a ratio of the molecular weight divided by the empirical weight. So you take the molecular mass in AMU divided by the empirical mass, and that gives you the factor that you need to multiply the empirical formula by to find the molecular formula. So you'll notice that in this problem, we have right here the molecular weight. So we know what this is. We need to calculate the empirical weight for our chromium oxide in order to find this scalar factor. So that's what we're going to do here. We know, because we've been told, that our empirical formula is Cr2O3. So to calculate our empirical weight, we look up the atomic mass of chromium, which is 51.996. The atomic mass of oxygen, which is 16.00, and we have to multiply chromium by 2, oxygen by 3. So let's see. 51.996 times 2 is 103.992. 16.0 times 3 is 48.00. You add these up, and it adds to 51.992. Now, sig figs wise, we're limited, because we're doing addition, to the second decimal place. So this number only has 5 significant digits, and this is our empirical formula, or our empirical weight. All right, so now we're going to use this to calculate the factor, scalar factor, that'll take us from our empirical formula to our molecular formula. So our molecular weight is 304 AMU. Our empirical weight is whoops, sorry, that's not where my decimal goes. 151.992 AMU. I'm leaving my number unrounded, though my denominator only has 5 sig figs. My numerator has 3, so that's going to limit us. Oh, it's a scalar factor. So actually, with this problem, we don't have to worry about sig figs. I'm just in the habit of always taking them into account, which is not a bad habit to be in this class. 304 divided by 151.992 gives us a scalar factor of 2.0001057. So this is a scalar factor of 2. So to find our molecular formula, we take our empirical formula, Cr2O3, and we multiply our subscripts by that scalar factor n. So we have Cr4O6, and this is our molecular formula. Awesome. Of course, dude. It is my pleasure. I'm glad. I'm totally glad you dropped by and livened up office hours. Honestly, the biggest thing I miss about teaching in person is all the human interactions, and I feel like office hours is as close as we can get in this kind of weird digital distance education world. So I'm always happy when I get some company up in here. Dude, I'm so glad that you find him helpful. Alrighty, well, that is about it for us. I gotta bounce to a another class. Ashley, thanks for coming out and asking some excellent questions today. I have one more office hour tomorrow morning, 8 to 9. Hope to see some of you there.